Hi, so my name is Ronald Swaraj, and I am a student from the Department of Mechanical Engineering at the University of the West Indies, St. Augustine campus. So today I will be presenting to you on a project that is currently being undertaken by a company called Ocean Energy Limited. So I think that name speaks for itself, right? Yeah. So when you hear renewable energy, when I hear renewable energy, the first two things that pop into my mind are solar and wind. Now, these guys down at Ocean Energy, what they are interested in is using the motion of the waves and converting that into energy. There are a number of wave energy models out there. The ones these guys use is called oscillating water column, and well, I will try to explain that now to you.
Okay, so this diagram here shows the basic model of an oscillating water column. As you can see, there's an opening to the ocean below the water level. This causes a column of air to be trapped above the water column. The wave motion, it could be modeled as a sinusoidal wave. So when the amplitude is high, the water will fill the column and the air will be forced up, which would cause the turbine to spin and generate electricity. Coincidentally, when the amplitude is low, the water level will retreat, air will be sucked back down into the column, and this will also cause the turbine to once again spin and generate electricity. Okay, so here you can see a slightly updated model of the oscillating water column, and this will be similar to the one the guys down at Ocean Energy will be using. So this is one of the rigs that they have offshore, which houses the oscillating column and its components. And well, I guess from this picture, you can see the kind of level of engineering that has to go into designing this. Now, one of the challenges they had was developing a power takeoff system. So what is a power takeoff system? The power takeoff system is simply a system taking power from an engine or motor and being able to transmit it to be used for some sort of application. This video here shows you a model of a power takeoff for oscillating water column. That up and down motion that guy is doing with his hand, that can be thought of as the trapped air going up and down. And as you can see, it is being converted by some sort of motor and it is producing electricity.
Okay, so that video there of the power takeoff system, that was a fairly simple example. The one Ocean Energy had to design, however, that was a bit more complicated. They had to be able to safely convert and dissipate the pneumatic energy from the action of the oscillating water column into electrical energy. It also had to be able to sense the sea conditions as a basis for starting the turbine. They had to be able to motor and maintain the turbine to a defined operational speed, as well as supervise the deceleration and shutdown of the turbine when sea conditions subsided. Now they had to also be able to monitor the system for errors, or when operation went out of the design range, and be able to take action to protect the system. The system also had to be able to log all relevant data for analysis. And it was also required to be able to operate and supervise the system remotely. So the turbine they use is what is called a Wells turbine. Now this is a low pressure air turbine which rotates continuously in one direction despite the direction of the airflow. This was particularly important because of the rising and falling water levels in the oscillating water column. The turbine itself is not a self-starting turbine, so they have to have an external power source on board the rig to be able to jumpstart the turbine. It also demonstrated some strong aerodynamics tool when the air velocity to tip ratios exceeded a certain value. Also, the turbine, it had a maximum design speed. If it exceeded this, the structural integrity of the turbine could be compromised. They therefore had to develop a fail-safe brake system on the turbine if the operations were to go beyond the design factors of the system. So to determine the rotational speed of the turbine, they use a reflective laser sensor. What this did is that it would generate short pulses each time a reflective element on the turbine passed a fixed sensor on the turbine duct. But they noticed some limitations with this. There was a low frequency of speed update at low rotational speeds. This meant that they would have a low and variable sample rate to input into the control system. Also, when the turbine was at rest, the sensor tended to output small, short signals because of vibration and wave motion. The sensor was also susceptible to errors because of ocean mist and foreign bodies that would tend to pass through the turbine duct. Now, it would have been very costly and time-consuming for them to go back and redo the system. So what they did was they recognized a less accurate but more consistent speed indicator was available from knowledge of the machine. By knowing the current, voltage, speed constant, and armature resistance, they could be able to calculate the speed that the turbine was supposed to be generating at. So what they did was they developed the control system to compare the two speed signals and be able to decide when to use a more accurate speed.
From tests conducted over a range of pneumatic input power levels, it was clear at high mean pneumatic input power levels and low rotational speeds, the aerodynamic stall characteristic of the turbine significantly reduced the power output. However, at lower mean pneumatic power inputs and lower turbine speeds, the power output was enhanced. Any further system design should prioritize robustness, maintainability, usability, environmental suitability, and safety. It is also important to note that there is limited access to the system for troubleshooting.